Welcome to this technical walkthrough of Nova Zenith, an interactive 3D web app for planetary exploration. This project aims to combine the engaging nature of immersive 3D graphics with modern and fluid interface design, resulting in a captivating educational experience. The platform consists of three main views: an interactive showroom in the center, a multi-body physics simulated view of the solar system's orbit, and a dynamic historical timeline. Today, I will be dissecting our HTML structures, styling through CSS and JS animation engines, and how all these elements make our code go. Let's begin with the main landing page. In index.setHTML, we set up a small footprint, DOM. The background is based on the HTML5 element whose ID is starfield. If we head over to script.js, you'll see our particle animation loop. The function in inistars uses the canvas, matches it with the size of the Windows viewport, and adds 400 unique star coordinate objects to an array to monitor the random placement, size, and individual velocity of these stars. The animate stars function uses a mathematical parallax. What we are doing is shifting the position of the star objects with an inverted scalar shift vector based on the relative position of the mouse X and mouse Y, to the absolute center of the viewport. This creates a sense of depth and interaction with the space when the mouse is moved. The use of request animation frame is to ensure that this engine runs at the correct refresh rate of the browser. The site uses Google's web component to display 3D graphics without the need for cumbersome third-party WebGL wrappers. Our JavaScript keeps the application state globally with a data structure that consists of a collection of planets with titles, descriptions, and custom binary asset strings. We store the global application state in a structured array of planets that includes titles, descriptions, and strings pointing to our custom BLIP, ADB, binary assets, in our JavaScript. If the user clicks on our left or right navigation labels, our update planet workflow will be fired. It resets text reveal effects, which come by removing the animate CSS class from the text. It uses a modular loop to ensure an infinite cyclic iteration over the array, and recalculates the array indices in the process. It then replaces the data parameters used under the hood, labels the neighbor button with special target orientations for more complex structures, such as Saturn's rings, and updates the information. We've also hooked up a load event listener on the model's event, so that it smoothly fades in once its 3D mesh has completely streamed into memory. If the user clicks Get Started, then a state class is added to the body of the document, which results in an elegant CSS layout shift. The hero text slides off screen using CSS keyframes, and the detailed description panel slides in as the 3D asset window is moved around. Switching to our special solar system page, solar.html, we have an automatically generated multi-body orbit layout. This is dynamically calculated in SolarScript.js, as opposed to a pre-programmed CSS animation path. Our planet specs dataset sets structural radius offsets, orbital velocity values, and physical scaling sizes. This is normal trigonometry using circular math and a continuous animation cycle loop. We calculate coordinates by using center x pesto, radius, and center y pesintha, radius 0.25. The 0.25 multiplier is applied to the y-axis at the same time to create the characteristic 3D elliptical tilt of the system. To prevent models from clipping unnaturally, we keep track of the sign of the angle. If it's positive, the planet is in the front, and we increase our standard z-index to 600. The shadowed sun element has a higher z-index, and if it's negative, it's in the back, and we reduce our standard z-index to 0. Let's take a quick look at this interactive historical timeline now. This page decodes certain planet entries from the URL query string with URL serigrams and dynamically maps the timeline's structural content into our layout container. The advanced scroll architecture uses three key web frameworks: Linus for smooth scrolling, Green Sock, GSAP, and GSAP Scroll Trigger plugin. For desktop environments, we use the pin.arch. As the user scrolls through the timeline on the left, Scroll trigger scrubs a synchronized timeline. The layout boundaries in the foreground image are gradually changed during each of the milestones transitions. With the clip path, inset 0, p, x 0, p, x 100%, 0, p, x animation mask. This will give a nice card wiping effect that will show the card below it. At the same time, the background color of the body gradually changes to the hex profile that's mapped in our dataset. A secondary 3D matrix effect has also been added to the image wrappers. When the user clicks on the image, the card tilts, and the normalized distance of the cursor is calculated and used to determine the real-time value of rotation X and rotation Y. To help preserve user experience in lower-tier mobile devices, the style sheets are using custom media break queries to flatten the DOM architecture, eliminate perspective-based 3D math, disable custom cursors, and throw away the layout and put it in a pure vertical stream. Nova Zenith combines the speed of hardware-accelerated CSS transformations with procedural math cycles of JavaScript code to achieve highly performance-optimized yet rich and interactive sci-fi designs. Thanks for hanging out, folks. Welcome to a live demonstration of Nova Zenith, an immersive interactive digital space designed to explore our solar system. Right here on the main landing page, you are immediately greeted by a responsive 3D planet showroom. As I move my cursor across the interface, notice how the star field shifts in the opposite direction. This dynamic parallax effect creates an immediate sense of depth, pulling the user into a cinematic space environment. Navigating the planets is entirely seamless. Clicking these left and right arrows switches between celestial bodies. The transition is beautifully synchronized. The descriptive text slides away, and the fully rendered 3D model fades and rotates into place. Users can see crucial planetary data, like its distance from the Sun and orbital period, right alongside the visual asset. Next, let's step back and look at the entire cosmic neighborhood by heading over to the solar system view. Here, the application shifts from an isolated showroom into a real-time moving model of the solar system. All 8 planets are rendered simultaneously, tracking along their individual designated orbital paths around a glowing central sun. What makes this view particularly striking is its sense of true three-dimensional perspective. As the planets orbit, they realistically scale up in size when moving into the foreground and shrink as they recede into the background. Furthermore, the layering is mathematically sound. Planets smoothly pass behind the sun's ambient glow and cross back over in front of it, mimicking a true orbital plane.